Influence of gallium doping on the morphology, structure, transmittance and energy gap band of Mg10 zinc 90O films obtained by spray pyrolysis.
As we know, ZnO is a promising candidate for future light emitting detecting and devices operating in the blue and ultraviolet regions due to its wide direct band gap of 3.37 electron volts at room temperature and a large exciton binding energy of 60 milli-electron volts. One of the most important approaches involved in designing optical and electrical confinement structure is bandgap engineering. ZnO has the capacity to form alloys with magnesium oxide. Since alloys made of ZnO and magnesium oxide provide a wide band gap, as mentioned above, the resulting semiconductor material has a highly tunable band gap, which can be controlled by the magnesium concentration over a wide range. Therefore, the magnesium atom is an important element in the ZnO-based optoelectronic and solar devices. From the various techniques used to produce magnesium-doped ZnO films, such as radiofrequency magnetron sputtering, we work with ultrasonic spray pyrolysis. This is an attractive method where large surface films with good uniformity can be made at low cost. In previous works on MgZnO thin films, the focus has been on the variation of optical, electrical, and structural properties. Results have shown that its band gap can be expanded as a function of magnesium composition. There are other studies on the effect of dopants inside structures. The results obtained by doping MgZnO with gallium are shown, and the effects of the gallium doping rate on the structural, optical, and morphological properties have been investigated. First things first, experimental details. Magna-10 and ZnO90 films were prepared by ultrasonic spray pyrolysis on quartz substrate. A solution of a methanol acetic acid and water, 80 to 10 to 10 respectively, was used to dilute 0.2 moles zinc acetate. The prepared solution was sprayed on the quartz substrate heated to 400 degrees for 60 minutes with a nitrogen carrier gas flow of 4 liters per minute. A set of MgZnO samples was studied. In the group, 99% magnesium acetate tetrahydrate was applied in a 10 atomic percent content as magnesium precursor and gallium contents of 0 to 6%. MgZnO doped with gallium to 0 at 6% films were studied with a heat treatment at 350% degrees for 3 hours in a nitrogen flow per 8 liters per minute. The first step of characterization is SEM. SEM morphology. To verify the morphology, a scanning electron microscopy used a scanning electron microscope SEM model JSM 7800 FGAOL with the Apollo X10 EDAX detector was also applied. The grand sizes were measured to know how this size changed depending on the percentage of gallium doping. As you can see, the behavior is non-monotonous with the minimum between 1 to 2% of gallium. The second step is X-ray diffraction. XRD used an expert MRD diffractometer was used to monitor the XRD patterns with a pixel detector and an angular resolution of 0.001 degrees. The X-ray beam came from cover source like 1.50,048 angstroms. Angle displacement with the omega 0.5 and omega 1 and omega 1.5 5 and omega-2. Where measured, it is shown that the studied samples has crystalline Wurtzite structure. Moreover, the most significant variation at the crystallographic in the planes 002, and the angle is omega-2 angle, and it is here where we can indicate safe displacement in diffraction peak 2 related to plane 002, as we can see in the figure of the results of the XRD study. The effect of peak 2 shift is displayed in the residual stress, which will be discussed later. The third step is transmittance. In this case, we use a carry 5000 UVBs near a spectrophotometer with deuterium arc UV light source and tungsten halogen visible lamp was used to monitor the transmittance spectra of the films in the wavelength range of 200 and 800 nanometers, which were analyzed using carry WIN UV software. As can be seen in the figure, the samples have a transmittance greater than 80%, which is very good to applications. So in the tau analysis, as can be seen in the energy gap table, the sample with the highest energy gap for these gallium doped samples is between 1% and 2%, due to the estimation of 3.47 electron volts and 3.45 electron volts for energy gap estimation. The fourth step is residual stress. It indicates that it is presently between 1% and 2%, where you have the smallest network constant. This directly influences the energy gap calculated by tau. There is a correlation here. The conclusions is the structure of gallium doped with MgZnO films, which were deposited by spray pyrolysis, has crystalline Wurtzite structure and high optical transmittance. When incorporating gallium, the diffraction angles and interplanar distance have a direct dependence on gallium as dopant. In addition, when gallium is 2%, both the maximum of energy gap and the minimum of the lattice parameter as a caveat. Furthermore, the minimum gain size is a caveat between 1% and 2% gallium when maintaining an optical transmittance of 85 to 90%, making it suitable for transparent conductive oxides. The latter suggests that 1% to 2% gallium as dopant stimulated the displacement of the X-ray diffraction in the plane 002 diffraction lines, whose behavior increases the energy gap and minimizes the residual stress.